Hello, can you hear? So good evening all. My name is Nidin Vinayakan, and yeah, I am a general software engineer, full stack software engineer working on different sections. I was mainly working on 3D engines and renderings. So I always try to push the limit of the JavaScript, mainly working on WebGL. And I was experiment with ASM.js before Wasm, so I have quite experience with the how these things works. And uh, I'm a fair as I'm a web developer, I tend to um, lean into the TypeScript because I like types because it somehow provide more performance because it you can actually know the some sort of issues before actually shipping the code. Then okay, WebAssembly came out, so I was experimenting with a prototype language called TurboScript, which actually add types to normal JavaScript. So we know types. It's actually strictly typed, not like in normal JavaScript. You cannot type any, or there is no undefined this kind of undefined behaviors. So we have type information in JavaScript. So technically, we can actually compile into a WebAssembly because WebAssembly has only specific types like integer 64 and 32 and float 32 and 64. So the TypeScript was a prototype. Then I actually dropped it. I didn't work on it. And a few of our friends work on AssemblyScript. So what is AssemblyScript? It's a TypeScript to WebAssembly compiler. And AssemblyScript compiles strictly TypeScript, basically JavaScript with types, to WebAssembly using binarian. So it's under the hood. It uses binarian to translate TypeScript code into WebAssembly. So we don't reinvent stuff. We actually build the abstract syntax tree and use binarian under the hood to compile to WebAssembly. And yeah, quite frankly, it generates like lean and mean WebAssembly. So you can just install AssemblyScript from npm. So it's just a very tiny compiler, and of course, dependency is binarian, and in the form of not by C++, but it used binary in JS. So it compiled binary into JavaScript and use it to compile TypeScript to WebAssembly. And let's look at the basic types of AssemblyScript. So in JavaScript, I think here very few web developers. So in JavaScript, we don't have any types specifically. We have 64-bit floating point number and object, which can be anything. It can change its shape at will. So, but WebAssembly doesn't work like that. It has only very specific, limited types. So we need to work with it. So instead of importing all the JavaScript awesomeness to the AssemblyScript, we restricted it. And yeah, it's actually directly map TypeScript type to WebAssembly. So these are the native types of AssemblyScript. It has integer, 32-bit, unsigned and signed, and 64-bit integer, both unsigned and signed, and floating point 32 and 64-bit. And there are emulator types because WebAssembly doesn't support it out of the box, but yeah, of course we can represent a 8-bit integer and 16-bit in 32-bit, so it doesn't not a big deal. And also Boolean with 1-bit unsigned integer. And there is target specific types for us. It's isize and usize. It's mainly for representing a pointer. So in 32-bit WebAssembly, it will be 32-bit integer, and in 64-bit, it will be 64-bit. But 64-bit WASM is not yet released. It's a future feature. So yeah, it's more like void, star, and size t in other languages. And a special type called void, so it's just indicate, okay, the function doesn't return anything, like in C++. And yeah, AssemblyScript has string, which is actually a static string. So it's represent string in UTF-16, not UTF-8, but it doesn't matter. So it's directly stored this string value into the memory. So like, as you see, in the memory, it will write the length of the string and the character code followed. So you can easily read it from either JavaScript or from WebAssembly. You don't need to worry about, because the compiler will take care of the address locations. And it supports array. So array is backed under the hood. It's actually backed by array buffer, like in JavaScript. So array array in AssemblyScript has, so you need to pass a type. So you cannot create any type array. So you need to specify what kind of elements in this array, and it must be same for the entire content of the array must be same type. And the memory structure of the arrays first will be pointed to a buffer, array buffer, and the length of the array, how many elements it contains. And let's look at the structure of array buffer. So array buffer, kind of the first 4 byte is actually length of the array buffer, how many bytes it has. And the next 4 byte, you just skip it for alignment. It's a 8-byte alignment. And then follow the n byte of the code. So it's just a basic. And yeah, and the interoperability with JavaScript, because from WebAssembly you cannot return a string or object to JavaScript, because it can only interchange numbers. And especially in WebAssembly, we have this 64-bit integer, which is not yet supported by JavaScript. But with the big int, it's coming, so we can actually pass 64-bit integer. But right now, you cannot pass 64-bit integer to JavaScript world, because it's just race exception. So if you are developing something in WebAssembly or AssemblyScript, if you are using integer 64, either you need to cast, like strip down the length or reinterpret it to 32-bit, so you will lose. So that's a big problem. But normal case, you don't need to pass 64-bit integer between JavaScript and WebAssembly. And all other, so in the 32-bit integers and 32-bit floating point and 64-bit floating point numbers, you can easily exchange between JavaScript and AssemblyScript, no problem. And all other objects like strings or classes, anything, you can actually pass it to JavaScript, but you only get a pointer to that object. Question?
Yeah. Can you put the int, the 64-bit one, and the 64-bit float, and then do type hunting?
Yeah, you can cast in AssemblyScript. Like you can cast a reinterpret, or there are different kind of transformation. So you can do same WebAssembly functions in AssemblyScript, like same like in normal WebAssembly. So you can actually reinterpret a 32-bit floating point into an integer. So you can do it.
Can you do it across like the WebAssembly JavaScript boundary? So you give JavaScript back something that is like.
Yeah, you can reinterpret that. Yeah, you can actually encode a 64-bit integer to 64-bit float and pass it to JavaScript. But mostly it will lose something, but at some boundary it will be okay. Anyway, you cannot do anything with the in JavaScript like operation, because you will lose some bit of information. If you do some operations with the 64-bit number in JavaScript, it might be you will get different result in JavaScript and WebAssembly.
Okay.
But you can do it. So yeah, so all the other objects, you will get a pointer when you call a function in AssemblyScript or WebAssembly. If it's returning a class or array or string, it will actually return a number. So you need to figure out, okay, how to read this from the memory. And we'll see it. How can we read it? And yeah, so variables in AssemblyScript, it's like normal TypeScript or JavaScript. So you can define constants and variables like global variables. And inside the function, you have, if you define var, it's actually a local variable. It can access from inside the different block scope. But if you put let, it's actually block scoped, so you can redefine it outside the block. So WebAssemblyScript compiler will handle it, like rename it and different variables. And so there will be no local variable collisions. And yeah, let's see how we can actually interact between AssemblyScript and JavaScript. Let's say in AssemblyScript, you have a class called color, which has 3 members, RGB. And I initialize a pixel, it's an array of colors. And I export a function called getPixel, and it return an array of color. So you can do any image processing or whatever you want inside the AssemblyScript. So in WebAssembly, if you want to read this data, so at the end we need to display something to the user. So let's say you need to do some filters in an image, and you pass the this original image to the WebAssembly. Then you do this filtering or black and white or whatever, and after you're done with that image, a pixel, you need to get it back and display into the HTML canvas. For that, so in the JavaScript part, you can actually use different methods for it. Here I use data view because it's very convenient, because using data view you can read different types of numbers from an array buffer. Oh, sorry. Second, sorry.
I think you need to restart the recording.
So I use data view because from data view I can actually read different types of numbers from the array buffer and pass little Indian or big Indian and the different offset. That's easy, convenient for now. So we have this WASM instance here. Let's say we initialize the WASM. You see how we can instantiate the WASM module. We have an instance now, so WASM instance, and it has exports. So we export this function, so you will get same function here. So let's call that get pixels, and you get a pixels pointer. So it's a number. It will be a 32-bit integer number. You saw already, because this is an array is backed by array buffer. I will go back here. Yeah, so this is an array, so array is backed by array buffer. So first element, in first 4 byte, it's the pointer to the array buffer, and the next 4 byte is the length of the array. Let's go back. So this is the pixel pointer. So we read the unsigned integer 32, which is the pointer to the array buffer. So we got the array buffer pointer. So the next 4 byte is the length of the array. So you can read the next 4 byte. So pixel pointer plus 4 byte. So you'll get the pixels length. So now we know that, okay, how many pixels are there. So let's create a float 32 array, length of pixel into 3, so it has 3 components. And yeah, just store this float size at 4. Okay, you can actually change it to 64, so you just change 4 to 8. And okay, so then we need to access each element of this pixel. So we have the array buffer pointer. So I will go back to the array buffer layout. So in the array buffer, first 4 byte is the length of the array buffer, and the next 4 byte is element 0. So here, array buffer pointer plus 8, the first 4 byte is the length, so we just skip it, and the next 4 byte element. Then you will get the pointer to the first element. So we have the number of pixels, so just put a for loop and just start reading the elements one by one. So from this element pointer, we'll get the pointer to the real color object or that class, which contains 3 elements RGB. So you can read, okay, it's float 32 numbers. So from the memory view, that data view, we can actually fetch, okay, get the first, this is R and GB. So increment by 4 byte. So you'll get the next pointer to the next element. So you read it until we complete the complete pixel. So in the pixels, we will get the result from the WebAssembly. It's actually, yeah, really not straightforward, but this is how we can actually read data from WebAssembly to JavaScript, raw data. If you want to read a string, you need to also do something like this. But in this string case, it's quite easy because we have the number length of the string. So you can actually create an unint 8 or unint 16, because in this case, in AssemblyScript case, it's this UTF-16. So you create a unint 16 array and pass the offset to the string and read. So you will get a unint 16 array with all the character code, and you can decode it. And the memory management in AssemblyScript, there are few memory allocators because WebAssembly doesn't provide any memory allocator, so you need to manage your memory yourself. So in AssemblyScript, whenever you use new some object, it will allocate a block of memory in the WebAssembly memory. So in previous case, let's go back. So you're creating new color. So it will, the WebAssembly compiler will calculate, okay, how many bytes it needs to allocate the color, and it will actually allocate this memory into the global WebAssembly memory, and it just increment the point offset pointer and return that pointer. The most important thing is there is no garbage collection like in JavaScript in WebAssembly. It's coming, but it will be slow. Then it doesn't make any sense to use Typescript with GC because it should, then it will be equal to normal JavaScript. So the point of AssemblyScript is, okay, just type like JavaScript and achieve the performance like C++. And yeah, to manage memory, okay, we create a pixels. It must be freed, otherwise the memory will leak. At the end, you will get a out of memory exception. And in the case of linking from other, because we can actually link C++ library to AssemblyScript. So you have a library which include allocator. You can actually import this module into AssemblyScript, and instead of these 3 allocators, you can just say import allocator/system. So it doesn't include any memory allocator. it just try to use the imported one. But if you are not importing, it will throw exception. So in this case, I need to free the pixel memory. So from JavaScript, you can go like a free. So we have this pixels pointer, just pass that pointer. And in the assembly script, it's not just pointer because it's an object, it's an array. It will automatically handle it. So if the pixel is not null, it will actually, because we cannot just delete the array pointer, because the array pointer is backed by array buffer, and in the array buffer we already create a lot of color objects. So we need to go through each object and free that memory. Yeah, it's not yet supported in AssemblyScript, but in the future you can actually just delete the array and it will automatically delete all the reference. Yeah.
When do you call it free? Like it's the user's tasks. Like the user is responsible.
Yeah, user is responsible for calling free.
So
or else we know how much memory we need. We can actually create like global objects, just reuse it instead of just creating, deleting. Just plan it. Okay, I need these objects, and just create in the beginning and just don't free it. Just run it forever. I will show you an example.
So, but like, how is this different from writing like good old C? There's like a lot of pointer arithmetic, free and like new and delete, do it yourself.
Yeah, it's not perfect, but the GC is coming. So let's say we can actually reference JavaScript object or use the GC and reference this object to the GC, and it will automatically handle the reference count and everything.
So you're using the JavaScript GC inside of the sample?
Not yet.
But
now,
it's an idea.
Yeah, it's an idea. So maybe this is painful, but for general number crunching and some algorithms, we don't need any class. In this specific case, if you are creating objects, you need to free. Otherwise, you need to allocate. You need to create this object up front and manage it. Also, if you're creating and deleting, the performance will be very low because you'll actually call a lot of this free and create. Then it will spend a lot of time to allocate this memory and deallocate it, and the memory will be like fragmented. There are a lot of other issues. Yeah. And right now, if you want to use these higher order objects, you need to free it. Otherwise, you'll soon hit the out of memory exception. And yeah, so you need to use the free memory. It's like free in C++ or other languages. And you need to just cast the object to usize, which is a pointer to the object, and just free it. And after freeing the elements, you need to free the array buffer. So you just load the this is the normal WebAssembly functions to load a number from the memory. So you just pass the pointer or the address of memory, and you can just load the data. So in this case, pixel pointer point to the array, but in this case it's actually loading the first element or first 4 byte from that address, which is actually array pointer, and you just free the array pointer, and finally you free the array. In this by this you actually free complete memory, which you actually allocated. Yeah, it's nasty.
But indeed, I mean, why not just go write a C program, compile it to WebAssembly, and let the runtime deal with all these things?
It's just for now. It's just an experiment.
I see the point, but
because yeah, initially I created this turbo script to study the WebAssembly, so internal. So by doing that, I studied the complete structure of WebAssembly, because in JavaScript it was actually standalone. It doesn't have any dependency. It was not using binary, so it actually translates from Typescript to directly WebAssembly code. So I need to create all of these sections, which other colleagues already explained, these different sections. So it was a nice experiment.
Mm-hmm.
This is AssemblyScript still an experiment, but yeah, let's see. So in Chrome Canary, there's already a shared memory available for WebAssembly, so you can actually create memory. It's actually worker-based threading. See, so you can actually create shared memory and pass this module to different web workers. So web worker actually run in different threads with the same memory. So you can actually do some heavy lifting with the WebAssembly. And yeah, how to initialize. So 2 GB is the hard limit now in browsers. So this is the number of pages they can allocate, and you just provide share it will true. So it will create a memory with shared array buffer underneath. And in the assembly script, you can actually pass the memory in ROM and module. Because when you import something, the first string is the module name, and the second is the import name. What's import name? And yeah, this is not so interesting, I guess. This is how we are actually allocating. So you have the base of the heap, and normally, right now in the assembly script, it's actually not supported. Shared memory is not yet supported in the master version because it stores the start offset in the global variable. So if you create another instance, that's actually local to that module. So if you allocate something, only that module know what's the top of the heap. So I made some changes, so it store the this offset, the allocator offset into memory. So you can use store and int 32, so it will store the pointer to this memory location in the shared memory. So all the threads are okay. When they allocate at the same time, there will be no race condition, and we cannot actually use the compare exchange, so it will not allocate two objects in the same memory. I mean, this shared memory is highly experimental. It's only available in Canary. And right now, working with shared memory is because whenever you create some variables, it's actually global variable. It's only local to that module. So if you want to share an object between threads, you need to write it into the memory. Because in AssemblyScript, if you create var, like this var context, it will define a global variable in that module. If you are not importing this global variable from different, also if you are mutating, because you cannot export mutable global variable, the global variables are local to each module. So if you change one global variable, it will not reflect to the other module. So in this case, I need to work with some data, so I create a class called context, and this is my shared data. It's colored. And in the main thread, I create a context, and yeah, I create this instantiate this class and return that class. And only the master worker will create context, and it will just pass this context to other workers. So you can set context with the different workers, so all the workers are in the same context. Otherwise, it will work on different contexts, different memory. Not memory, but different variables. So yeah, enough talking, just demo. So I created a path tracing in AssemblyScript. It's actually you might know the small PDs. It's a 99-line C++ code. I've actually brought into AssemblyScript. It actually trace as a small path tracer. It will actually calculate the global illumination. It's actually working in 7 threads, so it's doing multi-threading. Each, in this example, it divides the screen into 64-bit tiles. So each 64-bit tile is rendering in parallel in these 7 threads. And I have 8 threads. I actually left it one for the presentation. And this is not so fast because you can see it's taking almost half a second to render each frame. It should be like under 100 milliseconds. This is because WASM doesn't have complete map library. It doesn't have sine, cos, tan, this thing. Yeah. One way was I can actually use existing C++ library and import, but I didn't get enough time because it was like a overnight prototype. So I'm just calling the JavaScript sine cos. It's actually expensive. Also, there is no random number generator in WASM, so you need to implement your own or use JavaScript one. So it's calling for 3 JavaScript functions from WebAssembly. It might be the reason it's slow, and it's compiled with optimized by binarian, so it should be fairly optimized with optimized 3. But I don't know because I didn't do the benchmark with the JavaScript. This AssemblyScript can also compile to JavaScript as ASM.js. So I didn't do the benchmarking. Maybe next time I will come up with numbers. But at the end it works. So it was a fun project. And after, if I will let it run for a few minutes, it will generate something like this. Yeah, it's nice global illumination.
Like, why is it red on the left side?
It's a transparent, it's a glass. It's the, I forgot the name.
But the reflection then is black inside this.
Yeah, it's depending on how many bounds, because this is actually 4 bounds.
Okay.
So if you stop tracing after 4 bounds, it won't get the color. Yeah, that's why this is dark.
Okay.
Because for glass materials, you need like at least 9 to 10 bounces to see its actual, yeah. Yeah, that's end of the demo. Do you have any questions? Yeah.
So just a few short questions. I think we have to get out in like 10 minutes.
8.
Or 8 even. So maybe just...
Yeah, just a quick question. You said that garbage collector is coming for AssemblyScript or for WebAssembly?
It's actually optional, so you can use garbage collection
But for
or not.
AssemblyScript or for Web.
For WebAssembly. There's the proposal.
But then would not be predictable how we were saying, or would be predictable when the garbage collector comes.
Predictable in the sense?
In the sense that you don't know when the garbage collector will come and grab your...
Yeah, of course. In that case, there will be no point to compile Typescript to WebAssembly with garbage collector because it will be same like JavaScript. Yeah.
Yeah, maybe just to add languages like, I think, Rust and also, for example, Swift is currently not supported in WebAssembly, but there are languages that don't need a garbage collector, but also don't need or require you to do this kind of manual management of memory, which I think is not how we will write code in the future.
Yeah, no, definitely.
Yeah.
That was more like if one of the points of the WebAssembly was that, yeah, we have always predictable
but
and all of this, and then you add the garbage collector.
The garbage
I don't see
collector.
how can be predictable with the garbage collector.
I mean, the
What's
predictability is not the point of WebAssembly, right? Nobody says that it's predictable.
There was this thing that you
I
wanted.
think the garbage collector is only meant for languages that need a garbage collector. I think for TypeScript you wouldn't want to use a garbage collector because then the advantage of using typed without garbage collection language just goes away. Yeah? I think it's more experimental, and I would predict that things like automatic reference counting is the future for any language that compiles to WebAssembly if you want to use the performance. But if you want to, for example, compile Java or languages that require a garbage collector, it makes sense to share the garbage collector with JavaScript. It's not a performance issue because JavaScript and Java, they both just need a garbage collector to run.
I just want to back to
the confusion.
Compare it with C and C compiler and C language. Maybe one of advantages of AssemblyScript will be more tight control over the produced code that you have after, like on the compiled code, for final WebAssembly. Yes. Because you can explicitly call store, lower, and it's more explicit.
Yeah.
Context of
You can actually, without any JavaScript or TypeScript itself, you can actually use all the WebAssembly built-in functions in AssemblyScript, because it's all it provides all the built-in functions directly as it is. So you can, if you want to just write raw WebAssembly, you can write it with the AssemblyScript. So yeah.
So thanks for the talk. We have to get out in 5 minutes. I think quite interesting as a follow-up would be a talk about Rust, where all these memory management hassles are a bit simpler, I guess. I would also, in the future, like to see languages like Swift to come to WebAssembly. A lot of languages, I think, in the future will be supported, including Java. That is requires a garbage collector. This is more like supporting languages like Java. Yeah, thanks for coming.
Thank you all, and thank you Google to host this. And thank you all the coordinators.
Yeah, and I hope to see you next time with the talk about this.